Well, thank you very much, Anna, for that warm and generous welcome. It is a very great pleasure to be back in your wonderful capital city, and it is also a very great honour to be the Women in Physics lecturer this year for the Australian Institute of Physics. So what I'd like to tell you about this evening is I'm going to start by explaining what the LHC, the Large Hadron Collider, is. And then I want to give you an idea about why theoretical physicists like myself think that we might be able to make black holes, very tiny, tiny ones, at the LHC. And then if we do make them, I want to tell you about what will happen. And I hope it won't destroy the punchline if I tell you now that you can sleep easy in your beds, the world is not going to get swallowed up or anything like that. So first of all, the Large Hadron Collider. Now this is very much in the news at the moment. I actually saw a news item, I think yesterday, on this. What is it? It's the latest particle physics experiment at CERN. And CERN is the European Organisation for Nuclear Research. Now those of you who are on the ball will notice that the European Organisation for Nuclear Research doesn't spell CERN. It does in French. Okay. It's been going for about 55 years now, and at the moment there are 20 member states, which are the countries shaded in blue. Where is CERN? Well, it straddles the French-Swiss border just outside Geneva. So here we are, roughly speaking. If we zoom in, this is Lake Geneva, here's the city of Geneva, and the red splodge is, roughly speaking, the CERN site. And the experiment itself lies in a tunnel which is 27 kilometres in diameter. Here's an aerial view. I should tell you that if you go to Geneva, there isn't this white line on the surface. There's no indication that it's there. But it's in this tunnel, and here's the CERN site, and the border, roughly speaking, is there. So it's deep underground. Here's a picture of what it's like actually inside the tunnel. It's about just under 4 metres wide, and the pipe is actually in the middle here, and it's surrounded by some extremely strong magnets, and you can see one here before it went down into the tunnel. And what we do at CERN is we accelerate protons, and these are elementary particles that live inside the nucleus of atoms. And they're taken apart, and we have a beam of protons. And because protons are positively charged, they can be accelerated by going through a magnetic field. So hence all the magnets surrounding the pipe. So we whiz them round this 27-kilometre tunnel, and they go round and round and get faster and faster and faster until they're going at very close to the speed of light. And then we smash them into each other and see what happens. So this is a schematic diagram, and there are 4 points round the 27-kilometre tunnel where we smash the protons together. Now, there are 4 different detectors, one at each of these collision points. The ones of interest to us are called CMS, compact muon solenoid, and ATLAS, which is a rather less catchy acronym, but easier to say. Now, these are what we call general purpose detectors. So they're designed to detect all sorts of different particles. And essentially, whatever is made in these collisions, ATLAS and CMS are going to be able to detect it and work out what's going on. The other 2 detectors, ALICE is designed for when they're firing large ions around the tunnel instead of protons, and LHCb is to do a particular type of physics called B physics, so they're more specialised. So here's a picture of the ATLAS experiment, and I'm showing this one because my experimental colleagues at Sheffield are involved in this experiment. You can see it is incredibly complicated. And the diagram on the right-hand side is to give you an idea of scale. So the beam pipe goes through the centre here, The collision point is actually right there in the middle, and here, that little speck is a standard person. So it gives you an idea. We're talking about a detector that is very, very, very much bigger than the room that we're sitting in now. Very complicated, very large piece of equipment that's all that way underground. Now, of course, the LHC hasn't been built purposely to detect black holes. And I think over the next few years, it's going to be very exciting to see the results that come out of the LHC. And I think whatever they find, it is going to be exciting. And two of the things that they're primarily interested in finding, these are both simulations. First of all, it's the Higgs Boson, which, for reasons that I do not understand, the media insist on calling the God particle. Anyway, it's not the God particle, it's the Higgs Boson. And this is an important particle that we've not seen yet, that we think explains why all the other particles have mass. And this is a simulation of what it might look like if we make one of those in the CMS detector. The other big bit of new physics that they're looking for is supersymmetry. And this is a theory, it's a symmetry in particle physics in which every particle that we know about, that we've seen, has a partner particle that we haven't yet seen. So particles sort of come around in pairs. And this is a simulation in Atlas of what supersymmetry might look like at the LHC. Now, what I want you to take away from these two pictures is that physics at the LHC, these events are very complicated. There's a lot of particles. The tracks in the middle here are all particles. The curvature of the tracks tells you about the charge of the particles. And what we have out here are measurements of the amount of energy that those particles are carrying. So these are very complicated and difficult experiments. Analysing the data is going to be extremely challenging. So the LHC has been in formation really for a very long time. The very first workshop for this was over 25 years ago. And it took 10 years from that point to get through the technical description, technical design, to the council actually approving that this experiment was going to go ahead. Now, at that time, the 27-kilometre tunnel was actually being used by another particle physics experiment called LEP, the Large Electron-Proton and Positron Collider. And so they couldn't start building things in the tunnel until LEP had finished. So although they did work above ground, LEP didn't finish running until 2000. The first magnets went down into the tunnel in 2005. And you may remember a couple of years ago, 10th of September, there was a lot of excitement when they first switched on the machine and they managed to get the proton beams going round the tunnel. Now, those of you, if you're anything like me and you've done some practical physics experiments, you know the first thing that happens, you're doing a new experiment or you've got some new equipment, it doesn't work. Maybe that's just why I became a theorist, who knows? But anyway, so of course what happened, they switched it on, it was all very exciting, and then something broke. And they had problems with the magnets. Given the complexity of the experiment, this is inevitable. And they've spent a lot of work putting that right, and in November of last year, they got it restarted. And since then, progress has actually, I think, been astonishing. They've been ramping up the energy of the beams, and on the 30th of March, they had their first collisions, and since then they've been producing collisions. This week, there's actually a very big high-energy physics conference in Paris, and the media are reporting results from that from the LHC. And I should say that this is about half the ultimate energy that the LHC is going to run at. But they're going to run at 70 eV, I think, for at least another year. And just to prove it, this is not a simulation. This is a real event that they've seen at the LHC. Unfortunately, it's not a black hole, but you can't have everything. It's a side-on view, and again, you can see how complicated it is. Lots of particles created, lots of energy. We've got two big jets here, energy detected all over the place. But the real physics is happening, and it's very exciting. So, why have I put black holes and LHC in the same title of a talk? I need to say a little bit about quantum gravity first. There are two incredibly beautiful, very successful theories of fundamental physics. Quantum field theory is the theory of the very small. It governs atoms, it governs elementary particles. General relativity is the theory of the very big. It governs the motion of planets around the sun, the evolution of the universe itself. And both have been tested to what I think is extraordinary precision. So just to give you an idea, this is the catchily entitled E821 experiment at Brookhaven. Now, the LHC is big particle physics. Here's their ring, and there's your standard person. So this is a particle physics experiment that fits in a room, so a different scale. And what they're measuring here is something called the anomalous magnetic moment of the muon, which you don't need to worry too much about what it is. But it's something that you can calculate using quantum field theory, and it's something that they can measure at E821. And the graph on the right shows you the experimental results to date. Now, what you need to notice about this is that the discrepancies here in the experimental and theoretical values are at the order of 10 to the minus 9. At 1 part in 10 to the 9, the experiments are agreeing with the theory. I think that's extraordinary precision. Incredible. General relativity is a bit harder to test to that level of accuracy, but it's been tested at about the 1% level. First of all, famously using the Hulse-Taylor binary pulsar. So what you have here is you have two pulsars, very compact stars, that are orbiting round each other. And according to general relativity, as they go round each other, they will emit gravitational waves. And in doing so, they will lose energy and they will gradually spiral into each other. And pulsars emit this radio beacon that can be timed incredibly accurately. So it's possible to get very accurate information about the orbit of this binary pulsar. So this pulsar has been observed over a period of over 30 years. And the dots are the experimental data, and the line is the general relativity prediction. Beautiful agreement again, and this is what Hulse and Taylor got the Nobel Prize for back in the 1990s. More recently, it's been tested again at about the 1% level using Gravity Probe B, which is exploring the gravitational field of the Earth. And again, there's extraordinary agreement between the predictions of general relativity and the experimental results that they are getting. So these two theories are very successful, but they're fundamentally incompatible. And Einstein and subsequent physicists have spent a very long time trying to combine them and develop a more fundamental theory, a theory of quantum gravity. Now you might say, well, why do we need to combine them? One's the theory of the very small, one's the theory of the very big. They don't need to meet in the middle. Well, of course, most of the time they don't, but we'll see that they need to meet in the middle for black holes, which are general relativistic objects where you also need quantum theory, and also in the early universe, because the universe is very big because it's everything, but when it started out, it was very small. So you need both quantum field theory and general relativity in the early universe. Now, there's been an enormous amount of progress in developing a theory of quantum gravity, and there are many, many different approaches. I could spend a whole lecture just sort of listing them. Here are just a few. By far the biggest game in town in terms of the number of researchers working in that area is string theory. And what I'm going to be talking about today are ideas that are coming from string theory. And in string theory, the fundamental objects aren't point particles, but instead literally, I mean not this sort of string, but literally little strings that then vibrate. And one of the things about string theory is that if you do the maths, it naturally lives in more than the 3 space and 1 time dimension that we experience in everyday life. Now, these extra dimensions are going to be too small for us to see in our everyday experience. So it's like for us, a piece of paper is incredibly thin, but if you're an ant crawling on the paper, then its thickness is non-negligible. And I want to talk particularly about recent developments in string theory over the last 10 years or so, which are called brain world models. Now, brain world models come about as a solution of what's known as the hierarchy problem. So I should explain to you what this is. So standard model particle physics, the sort of physics that has been tested so beautifully at E821 and at CERN prior to the LHC, naturally happens at about 10 to the 2, about 100 or 1,000 GeV. And the next slide will give you a better idea of what that sort of energy scale is. However, gravity is very much weaker as a force than all the other forces in nature. So I can overcome the pull of the whole of the Earth, the gravitational pull of the whole of the Earth, just by the muscles in my arm, which I can assure you are not very strong. So gravity, quantum gravity, would naturally live at a scale of about 10 to the 19 GeV. So this is an awful lot bigger than this. And the question is why? Why are these two scales so different? Why is gravity so much weaker than all the other fundamental forces of physics? So just to give you an idea, roughly speaking, just to within an order of magnitude or two, 10 to the 2 GeV is just about the kinetic energy of a flying mosquito. So one of those flies into you, it's not going to do you a lot of damage. 10 to the 19 GeV is, roughly speaking, the kinetic energy of a cruising Airbus A380. I've got a confession at this point. I came on an Airbus A380, but it was actually a Singapore Airlines one. Okay, but you'll forgive me. Now, I certainly wouldn't want to stand in the way of a cruising Airbus A380. Okay, so that's what 17 orders of magnitude feels like. So what's the idea of brain worlds? The idea in brain worlds is that our universe is a brain, and that's a posh word for a slice, through some higher dimensional space-time that we call the bulk. And the key feature of brain worlds is that all the standard forces in atomic physics, electromagnetism, all the nuclear forces are somehow confined to live just on the brain. So particle physics only happens on the brain, and only gravitational degrees of freedom can propagate in the bulk. So what this means is that only gravity sees these higher dimensions, and this is why it's so much weaker, because it's getting diluted, because it's just got much more dimensions in which to live. So the consequence of this is that the fundamental higher dimensional scale of quantum gravity could be very much lower than the scale of quantum gravity that we see on our universe, on our slice. And it raises the exciting possibility that this could actually be as low as the energy scale of the LHC. And in particular, this raises the tantalizing possibility that we may be able to probe quantum gravity effects at the Large Hadron Collider, and in particular, black holes. So, what is a black hole? Roughly speaking, a black hole is a region of space and time where the force of gravity is so strong that nothing, not even light, can escape. These are not pictures, these are artists' impressions, but we have extremely good evidence that black holes exist in our universe, either in binary pairs with stars where they're sucking material off their companion star, or indeed in the centres of galaxies, including our own, the Milky Way. And of course, for me, one of the great joys of coming to Australia is the fact that you can go out at night and see the path of the Milky Way, which in the Northern Hemisphere we can't. So you're very lucky down here. So just to give you an idea of scale, we form a black hole when we squeeze some mass into a very, very small area. So if I was going to make a black hole that had the same mass as the Earth, I would need to compress the whole mass of the Earth into about that much. That's a lot of stuff in not very much space. If I was going to make a black hole of the mass of the Sun, I would need to compress all the mass of the Sun into a size smaller than Canberra. Galactic core black holes are rather larger. This looks like a big number, but it's not for that amount of matter. Now, here I'm not talking about these black holes, not even ones this big. I'm talking about mini, mini, mini black holes that are going to be smaller than the smallest subatomic scale that we know. So they're about 10 to the 4 times smaller than the size of a proton. Now, protons themselves, as we're going to collide at the LHC, are not elementary particles. They're made of other particles inside them, which we call partons. So there are 2 up, there's a down quark, and there are also some gluons inside them as well. So the idea about why we may make black holes at the LHC is in fact the same as this idea of squidging stuff into a very small area. So the idea is that if we've got 2 incoming particles that are going to collide at the LHC, and that the total energy, which is the same as mass in relativity, is in a small enough region, so these 2 are close enough together, then we will form one of these mini, mini black holes. And this is known as the Hoop Conjecture, which was first put forward by Kip Thorne in 1972. Now, in these brain world models, these black holes that we form are going to be higher dimensional because gravity sees these higher dimensions, so not just the dimensions of our universe. And what we're going to see on our universe, if you remember the picture a couple of slides ago, our universe was the yellow slice. And if this is our higher dimensional black hole, we're going to see what we call a brain black hole, which is effectively a slice through this in our universe. Now, a very good question at this point is, okay, well, how many black holes are you going to make? Well, this depends on a lot of things, a lot of which we don't know. It depends on what this energy scale of high dimensional quantum gravity is, which we don't know. It depends on how many extra dimensions there are, which we don't know. It depends on the energy of the colliding particles. This we do know, and we can measure that, so that's good. It depends on how close these particles get together, and that's something that we can model. It depends on the details of the structure of the colliding protons, how they're made up into those up and down quarks and so on, and that's something that's well understood. And it also depends on gravitational radiation that's going to be emitted as the black hole actually forms. And this is something that people are trying to calculate, but it's very, very difficult to get accurate estimates for. So there are some things we know and there are a lot of things that we don't know. And accordingly, the estimates of the production rate vary a lot. The most optimistic I have seen have been as high as 1 black hole per second. Now, in particle physics terms, that is an absolutely huge production rate. And people say the LHC is going to be a black hole factory. My own personal view is that I think this rate is a little bit optimistic. But in principle, at least, the LHC could be making a lot of these when it gets up to its full energy. So, the $64 million question. What happens if you make one of these things? Now, of course, one of the wonders of the internet is that it is completely unregulated. And this allows people who are scientists to express their views and to publish their research. And it allows people who are not scientists to also put forward their ideas about what is going to happen. And these are some pictures that I found, which is one particular person's idea of what might happen. So here's Lake Geneva, Geneva City, and this is the region where CERN is. And this is when we make the black hole, and the region gets sort of swallowed up a bit, and then it goes black, and then we get some starry stuff, and then we get space invaders. Okay. Excellent. The one message that I want you to take home this evening is that this is not going to happen. Okay? You do not need to... I mean, fortunately, you're here in Australia, so if there was a problem, you'd be the last to know about it. But that's not going to happen. And the reason that it's not going to happen is due to a very remarkable discovery, not by Homer Simpson, but by this gentleman here, by Stephen Hawking. And this is a picture of him actually visiting CERN, I think a couple of years ago, and you can see there are some of the magnets down in the tunnel. And what Hawking discovered is that black holes aren't so black, that in fact they're hot and they emit quantum thermal radiation. And unsurprisingly, this is now known as Hawking radiation. So black holes emit this quantum radiation, and these mini black holes that we're going to make at the LHC, or possibly going to make at the LHC, have an enormous temperature. They are incredibly hot. Just to give you an idea, the surface of the sun is at about 5,000 Kelvin. The solar corona is at millions of Kelvin. And here we're talking at about 10 to the 15 Kelvin. And the interesting thing about black holes is that their temperature is inversely proportional to their size. So what this means is that you have a black hole and it's radiating. So it's going to radiate, it's going to lose energy. And as it loses energy, energy and mass are the same in relativity, it starts to shrink. And therefore its temperature goes up. So it's going to radiate more quickly, so it'll shrink even faster, so its temperature will go up even quicker. And ultimately it will explode. So whereas unfortunately that's not coffee, but if I had a cup of coffee there, that will gradually get colder as the lecture goes on, as it radiates thermal radiation. A black hole actually gets hotter as it radiates thermal radiation. And this means that these mini black holes are around for incredibly short periods of time. Their lifetime's about 10 to the minus 26 seconds. So they're not going to swallow up the whole Earth. They're not around for long enough to swallow up anything, let alone the whole of Geneva. So that's meant to be reassuring. Now, what I've been doing as part of my research is to looking into, well, exactly what is going to happen in these black hole explosions. What are these going to look like in the detectors at the LHC? Now, when we form these black holes, initially they're going to be rotating very quickly because I've got two particles that are coming in like this, so we have some initial angular momentum. And by conservation of angular momentum, the black hole that we form is going to have some rotation. Initially, they're also going to be very asymmetric, and they're going to have attached to them what we call hair. So they're going to have some junk that's coming from the fact that the colliding partons have charge and colour and things like that. Now, theorists like me like to model what happens in the subsequent evolution in 4 distinct stages. Now, of course, in reality, it's not going to sort of say, right, I'm doing this now, and now I'm going to go and do something else. But nonetheless, it's helpful to get the key features. So the first stage is called the balding stage. And we expect that this stage is going to be a very small proportion of the lifetime of the black hole. And during this phase, the black hole loses its asymmetries, it emits gravitational radiation, and it also loses this hair, this junk that it's got associated with it. Now, in this stage, essentially we understand the physics. We understand the process of the emission of gravitational radiation. We understand the process of losing this gauge field hair. However, in practice, it is extremely difficult to do accurate simulations of this stage because the system is so asymmetric. At the end of this stage, we have a nice smooth black hole, but it's still going to be rotating very rapidly. And at this stage, we can start to consider the Hawking radiation of the black hole. So it's going to emit this thermal radiation, and initially it will lose angular momentum as well as mass, and we call this the spin down stage. At the end of this stage, the black hole has lost all its angular momentum. It's going to be spherically symmetric, and it will continue to emit Hawking radiation. We call this the Schwarzschild stage because there is a spherically symmetric Schwarzschild solution which describes a simple black hole of this type. So these 2 stages are essentially governed by the Hawking radiation, and that's what I've been looking at. At the end of this stage, at the very end of the life of the black hole, what happens is going to depend on the details of our theory of quantum gravity, which we don't know. And so the details here are kind of unknown, but it's going to be a very small part of the lifetime of the black hole. So what are the things that we're interested in the Hawking radiation stages? So first of all, we're interested in those particles that are emitted on the brain in our universe, because those are going to be the things that we can see in our detectors. And these are going to be all the ordinary particles of particle physics, the particles that you've seen in those pictures from CERN. Fermions, gauge bosons, and if they find it at CERN, the Higgs. There will also be gravitational particles, gravitons emitted in our universe, but we can't see those. And these are a bit easier to study because these live just on this yellow slice, which is our universe. But we're also interested in the particles that are emitted in the higher dimensions, in the bulk. Now, these are just going to be gravitational degrees of freedom because only gravity lives in the bulk. And we're not going to be able to see these. But it's still important that we know about these because these are going to contribute to what's called missing energy. So in particle physics, you know how much energy, you've put into your collision. And what happens is you add up all the energy and all the particles that you can see. And what you're left with is missing energy. So if we're going to get agreement with our models of black holes, we need to have a good understanding of what the missing energy is going to be. And the results that I've and collaborators have produced have fed into simulations of what black hole events might look like at the LHC. So we've seen already that physics at the LHC is really complicated. And in order to find things, you need to really know what you're looking for. So good simulations are really important. So here's a simulation of what a black hole event might look like at the LHC and the Atlas detector. This person wouldn't really be here. That's just to give you an idea of the size. Okay. So you can see that this is very complicated. We've got a large number of, I mean, if you just look in that middle bit there, huge numbers of particles being produced. And these events are very distinctive, so things like supersymmetry, Higgs, just won't produce as many particles. So the black hole events are very distinctive. So they'll have a good, hopefully, we'll have a good chance of finding them if they're there. Now you might say, okay, that's sort of fair enough, but this is all kind of based on theories really, you know, Hawking's radiation, it's a theory. How can I really be sure that actually one of these isn't going to swallow up the whole Earth? Well, the fact is that nature has already done the experiment for us in cosmic rays. So what are cosmic rays? Cosmic rays are highly energetic particles which bombard the Earth constantly from outer space. They've been observed with energies greater than 10 to the 11 GeV. Now, before you think, oh, well, that's many, many orders of magnitude more than the LHC, we need to do a little bit of relativity. So the Earth is a fixed stationary target, and we've got a cosmic ray coming in and hitting it. Now, you have to do a bit of relativity to work out what energy that's equivalent to if you've got two particles colliding head-on, which is what we have at the LHC. So this is equivalent to particles colliding head-on with an energy of about 10 to the 5 GeV. Okay? And this is an order of magnitude more than the LHC. So when the LHC is running at maximum energy, which it's not yet, it's going to be running at about 10 to the 4 GeV. And cosmic rays have been incredibly well studied for really quite a number of years now. Now this is, on the right hand side, I've got what's called the cosmic ray spectrum. So this shows the number of cosmic rays, the rate at which you find cosmic rays as a function of their energy. And you find fewer cosmic rays, the more energy that they have. So for example, up here, you end up with one cosmic ray at this energy hitting the Earth, hitting each square metre of the Earth every second. So that's quite a lot of cosmic rays. And then we come down here and we've got cosmic rays with this energy hitting 1 square metre of the Earth per year. Come down, 1 cosmic ray of this energy per square kilometre per year. And the very highest energy cosmic rays, so it's down here that we're at about 10 to the 11 GeV, you get one of these hitting the surface of the Earth per square kilometre per century. Okay? So if you're going to detect these, you need either a long time or a very big detector. But these have been detected. This is real data. First of all, there is the Agasa cosmic ray experiment, which covered 100 square kilometres. This was in Japan. And their highest energy cosmic ray event, which is about here, was at 2 times 10 to the 11 GeV. So they observed an event at greater than this order of magnitude more than the LHC. The state of the art in cosmic ray physics is the Pierre Auger Observatory. We don't have any Sheffield involvement in this, but at the University of Leeds, about 50 kilometres up the road, they're heavily involved with this. And this is a cosmic ray detector which has an array of detectors which cover an area of 4,000 square kilometres in the Argentinian Pampas. There's not a lot of stuff out there in the Argentinian Pampas, so it's quite a good place to build a 4,000 square kilometre array. And they also have seen events with energy greater than this order of magnitude energy more than the LHC. And here's a graph from one of their recent papers just to prove it. So this is an order of magnitude more than LHC energy. This is LHC energy. Okay. So why are cosmic rays relevant to this discussion? Well, the theories that tell us that we may be able to make black holes at the LHC also apply to collisions involving cosmic rays. So in other words, these brane world models will predict that cosmic rays will also produce mini black holes. And this will happen when the cosmic ray comes in and collides either with the Earth or with something in the atmosphere, or indeed other astronomical objects. And having formed this black hole, these ground arrays like the Pierre Auger Observatory will be able to observe the particles that are emitted afterwards. To date, there is absolutely no evidence whatsoever for black hole production in cosmic ray collisions. This is useful because it enables us to set a lower bound on this higher dimensional fundamental scale of quantum gravity. And it also, because of these cosmic ray collisions, over the surface of the Earth, over the whole lifetime of the Earth, there have been about 10 to the 22 collisions at or above the energy of the LHC. And this should be compared with over the lifetime of the LHC, we'll have about 10 to the 17 collisions at that sort of energy. So in other words, cosmic rays have already done the experiment 10 to the 5 times more times than we're going to do over the whole lifetime of the LHC. And last time I looked, the Earth is still here. So even if we do make black holes at the LHC, they will have been made in cosmic rays. The Earth is still here, the Sun's still here, so nothing disastrous is going to happen. So what I hope I've shown you this evening is that we really are entering a very exciting period in particle physics. It's a great time to be a young physicist and to get into particle physics. There's the potential to really discover new physics. It's also a great time to be a black hole physicist like myself, because recent developments in string theory suggest that we may be able to produce black holes at the LHC. And we may indeed be able to produce rather large numbers of them. If they are produced, they'll decay extremely rapidly. Very, very rapidly. They're not going to have time to swallow up anything at all. And we can already bound this process because of the experimental evidence and the experimental work in cosmic rays that's been going on for a number of years now. Now, when they first switched the LHC on in September 2008, certainly in the UK there was huge media interest. And I liked this cartoon. It's taken from the Daily Telegraph in the UK. I think the cartoonist was feeling a bit lazy and it was easy to draw. But what I hope I've reassured you is that the cartoon, the Earth, Geneva, nothing at all is going to get swallowed up by these black holes. Thank you very much.
So I'm sure Elizabeth would like to take some questions, or have maybe 10, 15 minutes of questions, if anybody's got some. Yes?
How do you actually detect a black hole when you've created one?
So the question is, how do you actually detect these black holes when you've created one? And of course, you've absolutely hit the nail on the head. That's the most important question. And the point is that you can't actually detect the black hole itself. All you can detect is what it decays into. All you can detect is this Hawking radiation that it gives off. And this is why it's been so important to really understand the Hawking radiation. And it's because the Hawking radiation doesn't look like any other sort of particle physics that we know about, at least, that will enable us to say, well, that's a black hole that we've formed.
Yes, on the top.
You just had the slide on before of 4 different states of the decay of a black hole. I probably won't understand a word you say, but what sort of tools do you use to model that sort of stuff?
That's a very good question. What a friend of mine calls hard sums. So how do we actually model these? Well, we have physical theories that govern various aspects of that. For example, tell us about the Hawking radiation. And we do some pen and paper calculations, and then we discover that it's too hard, and we have to put things on computer simulations. And to do calculations in these 2 stages, it kind of helps if you've got a network of computers, but you can do it on a PC. To do calculations of this sort of stage, where it's all rather messy, we actually do not have the numerical tools to do that yet. So in fact, if any young physicists want to make a mark for themselves, numerically, it's not because we don't understand the physics, it's because doing the calculations is too hard, and you really would need, you need a massive supercomputer to do it. To get the details of this stage, we need some inspiration. So again, homework. I like to give homework in my lectures. Homework, if you can find me a theory of quantum gravity and describe the details in there, that would be great. I leave Canberra on Saturday.
Yes.
Me?
Yeah.
This is coming from someone who knows nothing about physics. Great lecture though, thank you. However, when you're with the brain theory, you've got a black hole. Does that mean that there's actually more to the black hole than we can see? So it's actually more of like a 3D object?
Yes, absolutely.
Or I guess 3D is not the right word.
Absolutely. So you can think it is like, there we go. It is like if we, I have difficulty drawing in 2 dimensions. I can just about think in 3, and more than that defeats me. So let's suppose that the black hole was in fact 3-dimensional, but we were ants living on a piece of paper. So we could put a piece of paper and cut through it, and the ants on the piece of paper would just see kind of some of it, and they wouldn't see the bit that wasn't on the slice. So we're like the ants on the piece of paper, and there's more to it, you're quite right, that we can't see, that's not even in our universe. It's supposed to be mind-boggling, don't worry.
Yes.
Just following up on that, as I understand it, all the energy and momentum and so on conservation laws apply in the whole bulk, not just on the brain. But was that obvious? I mean, we invented or we discovered conservation laws in 3D, I presume, originally. And so was it obvious that some of it could leak out?
So the question was about conservation laws, conservation of energy and so on. And there is some experiment. We have no evidence for anything other than conservation of energy in our universe, okay, on the brain in our slice. So according to the theory, energy will be conserved, as you say, in the bulk, in the whole of this higher dimensional space-time. So this means that in our universe, in these processes, energy won't be conserved because some of it will leak out. Now, we have not yet got any experimental evidence of that sort of process happening. But one thing that I think it's worth saying is if you're doing particle physics at the LHC, you can't see all the ordinary particles that you make. So in particular, there are elementary particles called neutrinos, which can't be detected in these detectors. So it would be very difficult to distinguish between energy that you're losing, say, in neutrinos, and energy that you're losing into the into the bulk. So actually disentangling those effects is quite difficult.
Question right up there.
In one of the slides, you're saying that a lot of it was based on the string theory aspect. And there was a list of other ones like causal sets and that. Does this stuff still sort of appear in those other approaches as well? Like if, say, somebody's got their causal set hat on, right? And they're like, oh, no, I completely disagree with you because black holes of this sort don't appear in those causal sets. Is that going on?
Yeah, these predictions are unique to string theory. Now, there are lots of different approaches to quantum gravity, and of course at the moment we don't know which is the right one. Okay. So they've all got advantages and disadvantages, but really what we want is we'd like some experimental evidence. Now, of course, if we don't see black holes at the Large Hadron Collider, this is telling us something about these models coming from string theory. If we do see them, it's telling us that these models from string theory are correct, and the causal set people are going to have a lot of work to do.
Yes.
It was a fascinating lecture despite my desperately trying to keep up with the concepts. Thank you. I'm back to the question about detecting black holes, and you made the point that their sort of particular signature is that they emit Hawking radiation. I assume Hawking radiation is something quite distinct from other forms of energy that we're familiar with, in which case, how does one detect it? Because all our detection physics is based on knowledge about existing interactions, etc. So I'm just not clear how you actually detect Hawking radiation, or what form of radiation or energy it is.
Okay, that's a very good question. So, you know, what really is Hawking radiation? So Hawking radiation is in fact ordinary particles. It's ordinary radiation that we know about. So let me see if I can think of an example. Oh, let's go back to the cup of coffee, because that's something we can associate with. A hot cup of coffee emits thermal radiation. It is emitting infrared photons. Okay, so your black hole is going to emit photons, particles of light. It will emit electrons, it will emit quarks, all the ordinary particles that the LHC is designed to detect anyway.
So what's unique about its signature?
So what's unique about it is, A, you get an awful lot more particles than you do if, for example, you make a Higgs boson. And the other thing that's unique about them is how they are distributed. So if we think about, we've got two particles coming in and colliding like this. So you've got a preferred direction. So you'd expect that most of the time, actually, the particles that you produce are going to get sort of fired off in particular directions. A black hole, that's not true. So you can see, if you look in the middle here, all those particles are pretty evenly distributed. So that's quite different. So the particle physicists call that sphericity, which is very difficult to get your teeth around. But I think you can get the idea. So the events look different.
Thank you.
I'll take two more questions. I think you had your hand up first.
The picture that you showed shows that the black hole in 3 dimensions and that piece of paper as a universe. Does it mean that the black hole is somewhere else than the universe, and they're like something else than the universe, like a multiverse or something?
So it's not, these aren't multiverse ideas, which you may have heard about in cosmology. So the idea is there's just one universe, but there are, what we think of as our universe isn't the whole story, that there's kind of extra space. And you're quite right, the black hole is kind of extending into that extra space.
There's our doorway to that space?
Absolutely. So the black hole is kind of bigger than what we can just see in the universe.
Yes.
Are you going to smash any black holes into each other?
Oh. I wish I could. I wish I could. Actually, it's a very good point at which I can make. Of course, out there in our universe, nature is doing this. And nature is smashing some of these very large black holes into each other. And actually, that's what Susan and her colleagues here at ANU are trying to detect. But I think at the LHC, it's going to be incredibly exciting if we can find one and smashing them into each other. Maybe that's for the next particle collider.
All right, well, I think we'll close the questions at that point, and after we finish, perhaps a few people might like to come down and ask Elizabeth some other questions personally, and hand over to Joanne now to close.
Thank Elizabeth again for a fascinating talk.